In the previous video, nerds105, I was investigating the possibility of using multiple crystals in a crystal oscillator to bring down the phase noise. Now that failed because I was using wideband amplifiers, and with those I couldn't get a good limiter. So now I'm using different amplifiers with selectivity to see whether this idea was a good thing or not. So the whole thing is based on the fact that at the frequency of oscillation, the crystal is equivalent to an inductor in series with a resistor. And then in series with that, I put an amplifier with an input impedance that is low in relation to 80 ohms, about 20 ohms. When I put these things in parallel, I have just an inductor with 3 times lower inductance as seen for the resonance. Then there is losses, about 100 ohms, but anyway, this is an LC resonator, this capacitor, and the combined inductance of these. And then I couple energy into it through a fairly small capacitor like that. So that's the basic theory. The 3 crystals and the corresponding 3 amplifiers are within the blue frame here. So there are 3 of this. The input here, first there is a voltage divider, approximately half the voltage in this point, and then a phase reversal, so it comes in antiphase here. And then I have a small capacitor, a fairly much larger capacitor to ground that I can tune, and a small capacitor here. That is to feed an opposite phase signal that cancels the stray capacitance over the crystal. So that is to make a symmetric filter that attenuates rapidly on both sides. So there is the small coupling and the tuning, which is of course common to all the crystals. I want to load the crystal by about 20 ohms. So to do that, I have a J310. The input impedance here is about 70 ohms when there is an appropriate load on this side. And bring down the impedance by a bifilar winding on a binocular core material 61. It means that I get 70 ohms divided by 4 in this point, which is appropriate to load the crystal. With this coil, I get a very high impedance in this point. If I remove the crystals, the impedance here is about, rather high. On the crystal frequency, it is 4 times 70 ohms, or 4 times 80 ohms. It is a little bit different between the crystals. But the impedance of resonance is several kilo ohms. It means that the gain of the JFET is much higher on the crystal resonance than it is off. So the noise is a little bit lower off resonance than it is on resonance, but the noise figure of a base grounded J310 is very low. So this should be reasonably good, although it is not matched because the feeding impedance from the crystal is 4 times 80 ohms, and that's far above the 70 ohms where the noise figure is very low. But it's necessary to do a mismatch to get a high Q for the crystal. This is the second stage. It's common to all the 3 input amplifiers. It has a resonant circuit. I forgot there is a capacitor here. Just a small capacitor because I want a large LC ratio to have a high bandwidth on this one. And I have a tap. It is 65 turns and the tap is 15 turns up. And then I have a series resonance to put a suitable load, not exactly resistive, but the appropriate load here to feed the second stage. Is it 2 JFET in parallel? The reason is that the impedance here needed to present a low impedance at this point to the JFETs is 35 ohms. So rather than fiddling with the number of turns, I decided to just put 2 JFETs in parallel here. So they provide the appropriate load for this to give the appropriate impedance at this point. And then on the output from the FETs, I have a high Q resonator. It's a T80 of material 6, and it's only 12 turns of a fairly thick wire, 1.5 millimeter or something like that. And with 300 PF it gives a resonance at 10 megahertz and a fairly narrow bandwidth. More details about that later. And as a first test, I just put a single turn here on that core, and well, a single turn, a 50 ohm resistor, 50 ohms, and then I look at the phase noise with a phase noise analyzer at this point. Here is what I see after more than 24 hours. And I read just a few points from this. 1 Hertz minus 120 dBc per Hertz. 10 Hertz minus 150. And 100 Hertz minus 165. Or maybe 166. And then I see the limitations of the measurement system. This is internal interferences from the PN2060. And above 1 kilohertz, the result is incorrect, and that is shown by the circles on the data points. And exactly why? I think it's because the power is too low. It's only 2.7 dBm. So here, minus 185, that is below the thermal noise floor. But the measurement system has a noise figure. I don't know exactly how high, but in front of the PN2060 there is a 6 dB amplifier in each leg of the measurement system. So this is below what I can measure. Now it is only 1 turn on that output resonator, so the signal is low for that reason. I have 1 turn because then the output impedance is 50 ohms. Otherwise there would be big errors in the measurement since the signal level is so low. The measurement is with a Wenzel oscillator, fed the appropriate signal level into the selective amplifier that I have with the 3 crystals. What you see here is the result from the previous video, nerds105, and I can see here at 1 Hertz, minus 120. It's the same, it's the crosses here. The red dot is the result I had for the Wenzel oscillator only. So there is a small degradation. 1 Hertz from center, the filter response is still flat. What you see here is the frequency response of the filter. So the added noise from the crystals and the amplifier is very small. And then when the frequency offset is 10 Hertz, I had hoped attenuation of about 7 decibels or 8 decibels, but what I see is 150, so the added noise is much larger. Whether it is from my selective amplifier or if it is an limitation of the measurement system, I don't know. And then at 100 Hertz here, I was seeing now minus 165. That is here. But previously I was seeing minus 169, it seems. Well, I can look it up. Here are the old results, 120, 150 and 168.9. The many decimals come from the computer because I was using a pixel editor to find the pixels where the signals were. But now I'm not going to try to do accurate readings because it's accurate enough. And I have here now about 4 decibels worse result than I had when I was doing this measurement with the wideband amplifiers, but then I had a proper signal level. So this degradation is probably because the signal level into the PN2060 is too low now. Here is the impedance magnitude as a function of frequency. At 10 megahertz I have about 125 ohms. So it's the 50 ohm resistor, which is the impedance far away from resonance. The width here is 1 megahertz. So you can see 100 kilohertz on each side, then I'm down at 50 ohms fairly accurately. So this means that the carrier is suppressed because it comes from a higher impedance and it's the same electromotoric force if I had a high impedance load. Normally one would look at this with format, Smith chart. It looks like this. So it is 50 ohms, close to, but not on the resonance. There it is 125. I have added an amplitude limiter like this. On the high Q coil, I have put a bifilar wire, 1 turn, to get 2 turns like this. The midpoint gives a bias voltage for the basis of these transistors. There is a small ferrite bead on each one to stop oscillations in the VHF range. That does not affect the 10 megahertz signal because the impedance is very low at that low frequency. And then there is a coil on a ferrite core, and at the midpoint it is RF grounded. And I take out the signal through a series resonance link. By tuning this inductor I can change the phase just a little up and down. That is useful when it runs as an oscillator. But first I check what happens when I add this to the previous result that you had. Here again is the result without that limiter, and when I add the limiter I get this. Much higher noise level at high offsets. You can see it is here minus 170 nearly, and without the limiter it is below what I can measure. We can look at 1 Hertz here, minus 120, and here minus 120. So the noise does not degrade very close to the carrier. Of course, the level here is much higher than what we have here. So what I have added is a flat noise floor. If I look at 100 Hertz, it is minus 159 or so. With the limiter, and minus 165 without the limiter. So this was not a good solution. Maybe it is better if I give it a higher signal level. I have changed the number of turns here. It's 3 turns now of the bifilar wire. Here is what I see with 3 turns into the limiter. And here is what I had with just 1 turn. So it was a loss adding more turns, like this. Here again is what I have seen just with a single turn and a 47 ohm resistor. But now when the limiter is running, when I measure with the same directly on the high Q coil, I see this. The noise at 1 kHz has gone up significantly. It's minus 172 now, but before it was far below that. So the transistors, they introduce modulation on the high Q resonator. Of course, with the high Q, very small changes in the impedance, in the reactive impedance on that coil will change the frequency. So the transistors are frequency modulating, and of course that comes as a result on the output also. So here again is the result with 3 turns and the bipolar transistors. I replaced them by J310, not changing anything else, except that I could remove those ferrite pairs. And this is better, but not really good. So I have to do something else. I have to put a buffer amplifier to isolate the high Q coil from the next stage. I made a buffer amplifier like this, 3 turns into the base of a FET, and I take out the signal on the source and into a second FET, which has a gain of 3 with a transformer. And I take out the signal on the source where there is no amplitude gain, but the impedance is very low. So a 47 ohm resistor gives me a 37 ohm source for my test system. There is also this 1 turn with the 47 ohm resistor. And a very interesting thing is when I short this to ground, I make the Q much lower on this resonator, and I lose signal level, of course. Here is what I see with that buffer amplifier, and it's not particularly good. I have at 10 Hertz minus 146 should be 150, and at 100 Hertz it's 160, it should be 168 or something. When I short that 47 ohm resistor from the single turn, this is what I get. much better. 150 as it should be, and at 100 Hertz. But here you can see it goes the other way. I have degraded the Q so I don't suppress as well, and the signal level is also lower, so I get some noise maybe from that buffer. So the mechanism is clear. It's hard to take out the signal from a high Q resonator without disturbing it. And in this two measurements I have set the signal level to the same, about 3 decibels, because the performance of this PN2060 changes if I change the signal levels into it. Here again is what I saw with the buffer amplifier and with the signal level of 2.98 or 2.92 dBm into the PN2060. I have now made a new measurement using the full signal level here. It is 9.0 something dBm, and the difference is very small, but you can see here the interferences generated internally in the PN2060 have changed. They are higher here. But otherwise there is no clear difference. Maybe that the level at 10 Hertz is a little bit lower. I can look at what it says in here, minus 147, and here minus 146.2, 147.2. So this result seems to be 1 decibel better with the full signal level. So it means the performance of the PN2060 is likely in the neighborhood of minus 150. So maybe I should not hope for any better than that. I have been running Linrad in parallel simultaneously when I did this other measurement. So 147.2, 10 Hertz Linrad, minus 147, a little bit higher, a few tenths of dB. That's because here is 13 Hertz. 12.9 Hertz is the offset from 10 megahertz. So at 13 Hertz there is the notch from the sound card which cannot allow DC through. So the curve bends a little bit up here and it bends a little bit down here because there is a phase shift coming close to that notch. So I cannot trust the result at 10 Hertz too much. Then there is an interesting structure. At 700 Hertz there is this peak, and it is this peak, so it is a real signal of some kind. But in Linrad I see the noise floor going here, and then it is at a higher level here. I cannot explain what that might be, but I can see the level at 1 kilohertz is 167 plus something very small. And here at 1 kilohertz, if I read it, it says minus 166.4, and it seems to be well placed on the trace on the screen. And I can see that thing at 700 Hertz, also, so it is a real signal and not something that is produced internally in the PN2060. Here is the amplitude noise. It is much higher at large offsets, and it comes, of course, from the FET transistors. And if I look at amplitude and phase noise simultaneously, I can see that there is a correlation. Amplitude noise and phase noise are correlated. They are out of phase with each other, and at very close separations from the carrier, correlation is weak, because there the phase noise from the Wenzel oscillator is dominating. And I can see from the amplitude noise that the notch does not do much at 10 Hz, so the reading here was more or less correct for the phase noise. But already here there is a significant deviation. I have added 330 ohms here, thinking that capacitance variations here will be attenuated to not reach the high Q resonator as much as before. But on the other hand, the signal from here into the FET should not be attenuated, because the impedance of the source follower should be very high. But the resistor should add room temperature noise, of course. Already after 10 minutes I see a significant difference. This is what I have with the resistor in place, and here is what I had before. And there is a big difference at 10 kHz. And also here between 100 Hz and 1 kHz. And at 10 Hz it looks like I have lost performance. Well, perhaps not. I will have to wait for better statistics. Well, the 300 ohm resistor made a significant difference. So this is what I have with it in place, and this is what I had without it. But as compared with the result I had for a single turn directly on the resonator, is here. It is much better by 10 decibels at 1 kHz, and significantly better also here at 100 Hz. So it didn't solve the problem, it just indicated that it really comes from the buffer amplifier. Now that I found that having a high Q resonator at the output of the second stage is a bad idea, I have gone in the opposite direction and placed a resonator here with a Q of about 7. It's a T50 material 2 with 470 PF across it and 8 turns only, a small inductor adjustable in series for tuning, and it's loaded by 470 ohms. For a first test I put a secondary winding on that core, 3 turns, and to get 50 ohms at this point I had to add 33 ohms in series with 2 nanofarads. Here is what I see. Between 100 Hz and 1 kHz the noise goes down by 10 decibels, so this should be flicker noise. And if I go closer to the carrier, the noise increases slightly. So that is from the crystals probably. And then if I compare with what I had previously, that's this. You can see the noise is much lower at 1 kHz. That is probably due to mismatch problems. and above that frequency there are only errors because of mismatch. The level was fairly low, only 2.7 dBm, but I think this result above 100 Hz or so is just incorrect because of impedance issues. But here I have corrected the impedance over the entire frequency range up to about 100 kHz or even a little more. But at 1 MHz this output impedance drifts off, and also the level is probably lower because of the selectivity. But what happens above 100 kHz is not very interesting, I think. One thing, if you look at the 0.1 Hz back here, it has degraded slightly. I don't know if it's really meaningful, but it could be, and if so, it is probably due to infrasound, because I haven't put the lid on properly. As you can see, I can move here a little bit. This means that pressure variations can enter the box this way, but only at low frequencies. Doing it this way, I completely get rid of the electromagnetic interference, and I was a bit lazy, and it's not important for what I'm looking for. I have had Linrad running in parallel, and it's clear all the way from maybe 20 Hz up to 1 kHz. I have a very strong correlation between amplitude noise and phase noise, and I can see that the phase angle is close to 90 degrees. The amplitude noise is a little bit stronger, and as the amplitude changes, the capacitance changes and produces a modulation which is phase shifted. But since correlation is very high, I can say that the phase noise here is caused by the current variations that produce this amplitude modulation. Whether that depends on the signal level or not, I will investigate by now changing the signal level by 10 decibels. Here is what I see with a 10 decibel lower input signal. I have attenuated from the Wenzel oscillator. And as expected, the noise floor here at the large separation has gone down by almost 10 decibels, or rather exactly 10 decibels. And also the noise at even further separations. But at 1 kHz here, the noise has increased by only 0.4 or maybe 0.5 decibels, and at 100 Hz the difference is very small. But then again at 10 Hz the difference is larger, and finally at 1 Hz there is no difference. And I interpret this as, of course, this is amplifier noise, 10 decibels. Here is the flicker noise from an amplifier, and it hasn't changed much. The amplitude modulation introduced by the amplifier seems to be independent of the signal level. What I see here, I think this is thermal noise that dominates at this offset. And at 1 Hz, I see the noise of the Wenzel oscillator, which doesn't change when I change the level. And here, the difference is small, and statistics is not good enough to say anything. Here is what I see in Linrad, looking at the correlation and amplitude and noise spectra at the same time. I can see that the level difference is only 1 decibel out here, and I can see this curve is not the same as I had before, which is here. This is about 2 decibels now, and here this is flat and at a higher level. What I see is that the relation between flicker noise and white noise has become different. The white noise has increased because of the change of the signal level, a lower signal level, but the modulation is the same. That is, the flicker noise changes the capacitance and the gain through the transistor, and that doesn't change when the signal level is changed. That's the conclusion I can draw from this. I have marked the significant changes here. Of course, at large separations there is 10 decibels. That is white noise from the amplifier, the last stage. Then, at 1 kilohertz and 100 hertz, the correlation is a little weaker. And at 10 hertz, there is a big difference, about 6 decibels. And I guess this is thermal noise from the crystal. Or maybe noise from the input amplifiers, seeing a different impedance a little bit aside from the carrier. The impedance is lower here than it is at 100 Hz, and therefore the amplifier might give more noise, or at least it will amplify the crystal noise more, since the impedance is lower here as compared to here. And of course, close to the carrier, the Wenzel oscillator dominates. I don't see the thermal noise. I have placed the 330 ohm resistor here. It has reduced the supply voltage from 15.7 volts to 7.7 volts. And I have not decoupled this point for low frequencies, not yet. And since I don't know what causes the noise modulation in this kind of amplifiers, I'm just testing everything that I could change to see what matters or what does not matter. Here is what I see with the 300 ohm resistors in place. The drain voltage is about half what it was before. And here is the previous. It has been a longer time. 1260 here and 240 here only. So this has a much worse statistics. But the difference, if any, is very small. This isn't really showing a degradation. Maybe just a little if you look here. Could be 1 decibel, but not here. Half a decibel maybe. So that's not significant. Flicker noise is varying current through a transistor, causing modulation of the signal the transistor is amplifying. Now I think it comes from this amplifier stage with 2 J110. I put this resistor there and it made no difference, but the 1/F current would create a voltage drop that varies across this resistor. So I have placed now a big capacitor, 4700 microfarads at this point, to make the voltage here constant, even though the current through the transistors might vary a little bit. Here is the result with the lower voltage and the big capacitor. And here is what I had with 16 volts feeding the amplifier. And there is no difference. Except here. Now the result has improved at 0.1 Hz. But at other frequencies I see no difference. And the reason for an improvement at 0.1 Hz is I have put the lid on properly, so infrasound doesn't get in anymore. I have restored full supply voltage for the drains of these transistors, but I have added now a second 470 ohm resistor to load the output resonator, and this has reduced the signal level by about 4 decibels. Here is what I see after 15 minutes, and the old long time result here, it looks like I have a significant improvement. It goes something like this, and maybe 2 decibels below. Hard to say, I have to wait some time. When I changed the load on the output resonator from 470 to 235 ohms, this is the result I have after some time. Previously, this is what I had. So there is a significant improvement. If you look here at 1 kilohertz, it goes down from here. So it's about 6 decibels better at 1 kilohertz. At 100 hertz, maybe 5 decibels. And even at 10 hertz, 2 decibels approximately. But at 1 hertz, there is no difference. And again, here I have also now a proper closing of the box so the infrasound doesn't get in. But when I look at 1 megahertz out here, there is more noise now. Maybe that is because the signal level is low. It is now 3.8 dBm. Previously it was 8.5. So I've lost more than about 5 dB, not 4 as I said before. But the flat noise floor extends all the way down to about 7 kilohertz now. Previously it was going down to about 70 kilohertz. When I look at the correlation with Linrad, I see that at lower offsets, maybe 50 hertz or so, the correlation is much smaller. But it is very noisy now. And the correlation increases when I go up to about 1.5 kilohertz or 1.2 kilohertz or what I have here. And if I look at the level, firstly, it is very noisy here because the signal level into Linrad is a bit low now. If I compare with what I had before with the 470 ohm resistor, it looks like this. And you can see the noise level was much higher and correlation much greater. So this is really a significant advantage, although I will have to boost the power level with one more amplifier if I go this way. I have added an amplitude limiter like this with two BFR91A. Here is the phase noise at the output of that limiter, and I compare it with what I had before. Here is with 470 ohms on the buffer amplifier, and here is with the limiter. You can see I have added some phase noise above 1 kilohertz, and when I lowered that resistor from 470 to 235, I got the flat noise floor down here, but now I have an increased flat noise floor, and probably the this here comes from the buffer amplifier. But that doesn't matter, it will not pass through the crystal when I use this signal for feedback. What is important is the noise below, maybe 20 Hz or so. And here I have not lost anything. And here is the infrasound problem I had, which I don't have anymore because this time I've also put the lid back properly. Here is phase noise and amplitude noise as I can see with Linrad. This looks very different from before, as you can see. The phase noise is low, but the amplitude noise is pretty high. And I don't like to have the amplitude noise significantly stronger than the phase noise within the passband of the crystal. So I will try to reduce the amplitude noise. This transistor, BFR91A, have very low capacitances, and I guess that is why current variations that give amplitude noise do not couple to the phase. And here I can see amplitude and phase noise are not correlated, except here, but not very much. I have placed 4700 microfarads here to stabilize the DC voltage on the basis. Already after 25 minutes I see a big difference. The amplitude noise is now much lower than the phase noise. And at 10 Hz, probably statistics is not good enough yet. Well, here is amplitude noise only, and I can see the imaginary part, the red dots, are stronger or equally strong as the amplitude noise. So the amplitude noise is well below here. And I can compare with what I had without that big capacitor. That's here. And you see it's a big difference. I put my finger here when they cross. And of course phase noise is the same, but amplitude noise is down here. And now I know it's even lower. I have removed the big capacitor here and reduced the impedance of the voltage divider by a little more than a factor of 5. So that should reduce the sideband noise by a factor of 25, 14 decibels or about that. And that should be enough. I want the amplitude stability to be good all the way down to DC, because there could be some amplitude to frequency conversion in the crystal. And I also changed from two 407 in parallel to a single 220 ohm resistor. From 235 to 220 ohm, I don't think that will make any noticeable change. I have been running for 5 hours 40 minutes. That's enough to see the amplitude noise well up to about 20 Hz. And then there is a region where it is too noisy. And then it's visible well above 100 Hz. And when I look here, I can see that the amplitude noise is below the phase noise up to about 10 Hz. And at 10 Hz, the filter produced by the crystals suppresses the amplitude noise quite a bit. So I don't think this is harmful. And what happens at higher offsets is not critical because it doesn't go through the crystal filter. When I look here, I can see that the correlation, the sign is reversed now as compared to what I've seen before. When looking directly, well, I don't remember exactly where I had it. And here is the phase noise, and I compare with what I had directly from the buffer amplifier before. It's here, and this was with the 470 ohm resistor, and it's now a little bit lower here. This is the ongoing measurement here, and that's the old one. And if I look at 10 Hertz, it is very much the same, and the same here. But here is a problem. A significant change at 0.1 Hertz offset. I have to do this once more. Maybe I have had some interference of some kind. I mean a mechanical problem or whatever. Well, the problem is reproducible. The phase noise at 0.1 Hertz is very high now. It has got up by about 15 decibels. And such a low frequency of phase modulation, I cannot see why it can be caused by my changes to the biasing of the amplitude limiter. Now I'm looking directly on the Wenzel oscillator, and then I compare with my old results, and I have the problem at 0.1 Hertz. So something has happened to the Wenzel, probably to the power supply I'm using for it. I have added a low-pass filter in the power supply line, 8 ohms and 2 farads. And now the problem at 0.1 Hertz has disappeared. We are here, and this is the old result. And up here the difference is small, but here the filter is not very active anymore. So I have a problem in the power supply. Is this power supply? It has been running continuously for maybe 2 years now. And suddenly something goes wrong with it. Here is 8 ohms, and the Wenzel is in another room. I have made a third amplifier stage like this. More than one JFET, J310. And this resistor, I have tried some different values. These capacitors, this one and that one, are adjusted to make the impedance resistive in this point and in this point. And here it is 50 ohms all the time. And I have varied the number of turns to achieve that while doing these experiments. Not much, but the final was 14 turns. While doing these experiments, I have also adjusted this resistor, the buffer resistor, which has been 470 ohms, and then I changed to 220. And I tried some different values. And also for this output resistor. And while doing these experiments, I have disconnected the limiter, because when I had a high Q resonator here, the limiter introduced noise into the resonator. So I have removed these two connections, so the bifilar winding here is open. And I will connect it after having optimized to see whether it adds some noise or not. Here is the performance measured at the output of the buffer amplifier with a buffer resistor of 470 ohms, and there is no third stage. I have shown this before. And what's interesting here is the flicker noise that comes here. And also the very low, wide, flat noise floor. When I changed the buffer resistor to 220 ohms and also added the third amplifier stage, the flicker noise is much lower, but the flat noise floor is significantly higher. I go back to the previous. You can see here, and you can see here. It has gone down. Not so much, but significantly. Here, 162. And here, maybe 167. Here I was using 2 transistors, 2 FETs in the third stage. I changed that to 3 FETs, and at the same time I made the buffer resistor 330 ohms. And you can see I have gained something here, but I didn't really lose anything in the flicker noise region. Maybe a little, not much. Going from 3 FETs here to 4 FETs makes a very small difference, but in the right direction. In this I have had the output resistor 2.2 kilo ohm. I have reduced it to 1 kilo ohm, keeping 4 FETs, and that's here. And it's a trifle better, not much, but just a little. Having more FETs puts a higher load on the transformer at the output of the second stage, and that reduces flicker noise a little bit. I do not have the wideband noise comparable to what I had with 470 ohm and directly on the second stage, which was this. But I have lost about 5 decibels here at 20 kilohertz, 30 kilohertz. On the other hand, looking here around 100 hertz, this is what we have directly with the 470 ohm. Now, this is significantly better. You can see the flat noise floor goes all the way down to 1 kilohertz, where it has lifted by about 1 decibel. Before, the flat noise floor was much better, but it extended out to 30 kilohertz, where it was 1 dB lifted by the flicker noise. I have reconnected the limiter, and here is what I see when it is in place. And without it, like this, with limiter, without limiter, with limiter, without limiter. And you can see there are no changes all the way until I come here. Now this is with the limiter, without the limiter. Cannot imagine this is caused by the limiter. It means frequency variations over time periods of 100 seconds. I think this has to be a continuing degradation of the power supply. With a filter, 8 ohms and 2 farads, the change is very small at 0.1 hertz, because that is a really high time constant. But for 100 seconds it doesn't have much influence. So with the limiter in place, I can turn the unit into an oscillator and see whether this problem disappears. Now I'm running the selective amplifier as an oscillator. The signal level 9.9 dBm. It was before 9.2 dBm, so the signal level is 0.7 decibels higher. That's really a very small difference, but that is probably the reason why the wide noise floor is a trifle better. Very small difference, probably 0.7 decibels. At 10 Hz, performance has improved, not much, but it is a little better than -150. At 1 Hz, the difference is also small, but closer to the carrier, there is a degradation, probably caused by the supply voltage that is noisy to some extent. I don't know yet, I will try to find out. The Linrad screen shows me there is a significant amount of amplitude noise, and the correlation is not so strong, but there is some correlation between AM and phase modulation. Here the signal is too noisy, but there is a correlation I can see, and it is so noisy here in the real part. I don't know exactly why that is more noisy than the imaginary. The RC filter in the power supply line was 19 ohms and 0.7 farads. I have increased the resistor to 28 ohms, and this is the result, and it doesn't differ very much. Maybe there is a small improvement here. And then I have increased the capacitor. So now the total capacitance is 1.6 farads. And then here is what I see. And I can see a difference here. If you look at the slope of the average line here, it is so noisy, so we cannot just read a single point. And here it is clearly below. And if I look for the performance of the filter in this image has an attenuation of 9 decibels at 0.01 Hz. And here the attenuation is 4 decibels. So if the noise from the power supply is dominating, I should expect a difference of 5 decibels here. And that might be fairly close to what I can see. At 0.1 Hz, that's here, the attenuation should have increased from 22 decibels to 28 decibels. But the difference I can observe is very small, which means that more capacitors or bigger resistance in the RC filter would not change. So this is the noise of the oscillator itself. And of course, here the filter is low pass filtering enough. So what I see is the oscillator performance. Or maybe there is a leakage current that is a little bit noisy among all those big capacitors. That's a thing that is very hard to judge. So anyway, This is with the extra big capacitors. So this should have a lower level here. But it looks more like the opposite. But it's hard to say because statistics is not really good enough. The input impedance of the first stage here is very close to 50 ohms. Very little energy goes into the crystals. And the output impedance of the limiter stage is also very close to 50 ohms. These two resistors come in parallel because of the transformer. And this is a very low impedance. It's just to adjust the phase slightly. So when I connect a 50 ohm dummy load at this point, I will load the limiter by 25 ohms instead. And that reduces the signal level by 6 decibels. And the noise performance I see, of course the flat noise floor here is degraded by about 6 decibels. But also at close separations from the carrier, I have a similar loss of performance. Maybe not quite 6, but 5. So higher levels in the crystals might be interesting. They are specified 0.1 milliwatt each. I have removed the dummy load and readjusted the attenuators, so now I see 9.09 dBm. And I put it back and it goes down to 2.3. So that is the reduced level I have got. 9 minus 2.3. The 3-crystal oscillator has been running for about 30 hours now. The result I see is approximately what I expected, above about 3 Hz offset. I can compare it with the Wenzel oscillator, which I have here, and you can see the difference is about 5 decibels at 10 Hz and also at 100 Hz. Higher up, the difference is not related to the number of crystals, I guess. Maybe because this high power level from them, but comparing to the Wenzel, assuming that the Wenzel is an ideal design, I should think that is reasonable in the close range, but not for the flat noise floor. But what I see, an interesting and discouraging thing, is what happens very close to the carrier. Here, this is my oscillator, and here is the Wenzel. And the Wenzel is better here, but at 0.01 Hz it's the other way around. I don't know whether this is a phase instability in my oscillator, could be caused by a limiter or some other amplifier stage. And at 1 Hz I had expected a little bit better than minus 122. I had expected minus 124 or 5 or so. Here is the result I had when using the 3-crystal unit as a selective amplifier. And it's a bit interesting to see here. At 1 Hz I had the noise from the Wenzel, and here is what I have when it is an oscillator. But at 0.1 Hz I have the stability of the Wenzel and a degradation when using this as an oscillator. And even closer, there is not much difference. It's all a bit confusing. Now I want to investigate whether this idea of using 3 crystals with separate amplifiers really improves anything. So what I will do is to connect this point to that point to that point, which means 3 crystals in parallel, and then the amplifiers in parallel, which is essentially an amplifier with more transistors in parallel. To do this, I have simply connected this point to the same point for all 3 of these groups. Here is the result, and I can compare it with what I had when running the 3 first stages not connected to each other. That's here. And it's very similar, more or less exactly the same, all the way up to here. But then, this point, it has improved after I put the input stages in parallel. That is a little bit hard to understand. I can guess perhaps the electrolytic capacitors I added recently have become more stable now. A couple of days running at full voltage, 16 volts. So I will disconnect the wire between the 3 input amplifiers to see whether I get back this or whether the stability at a 10-second time scale still has improved. Note that the signal level, which we have here, and the frequency, which we have here, did not change significantly. This is with the 3 stages in parallel, 14.00 and 13.998. And the signal level 9.127, 9.080. So the signal at the points which I connected together are very similar, as they should be. I have removed the wire that connects the 3 crystals in parallel. And here is what I see now. The additional noise I had at this place, 0.1 Hertz, is gone. Here is with the 3 crystals in parallel, and here is the original configuration. And now they look very similar. Actually, perhaps this is a trifle better. But if I look here, 121.8 and 121.8, 51.2, 50.8, well, 10 Hertz. If we look at the curve, it's certainly not clear that there is any difference. But up here, this is a little bit better. This is with separate crystals, and here is with the crystals in parallel. Now it's so noisy, so I cannot draw any conclusion. You can see that there are small circles all the way, and here also. This means that the data is not valid. That's because the imaginary part is equally strong as the real part. So this is just statistics. So the conclusion is that there is no advantage of having separate amplifiers for the 3 crystals. discouraging, but that's what I see. Now, I don't have separate amplifiers for the whole amplifier chain, only the first stage. If I had 3 complete chains with all the amplifiers all the way up to the limiter, I'm pretty sure the noise would be a little bit better in the region where I have flicker noise, because I know that flicker noise is generated by not the first stage, what I see somewhere here. I don't know, but perhaps also the flat noise floor would improve if I had separate amplifiers after the first stage. But that is a lot of soldering, and I'm not really so interested in this. I was hoping for an improvement in the close range noise, where noise is probably generated by the crystal. Here is the Allan deviation of my 3 crystal oscillator. It is significantly better than my 2 oscillators, channel 1 green, channel 2 red. The channel 1 is more noisy. I have had to lock it with a significantly shorter time constant than what I can use for channel 2. So the time constant of channel 2 is about 20 times longer, which means that up to 20 times this point, which is 10 times, 20 times about here, the 2 oscillators are independent. The green points are following the rubidium source, and the yellow, they don't, because they have the noise of the channel 2 oscillator. So they should be independent, although it doesn't look so when I look here. The yellow trace is the correlation between these 2, and that is the performance of my 3 crystal oscillator. And I can see frequency versus time. You can see the slow frequency drift here. That is the slow frequency drift of my oscillator. And you can see sometimes there is some correlation between red and green. The green trace has much more rapid variations. That's the noise of the channel 1 oscillator. Variations of channel 2 are much slower. And that is a combination of my 3 crystal oscillator and the noise of the channel 2 oscillator. It seems it will be a good idea to replace the channel 1 oscillator by this new oscillator and start doing experiments with a better system that will have a faster convergence for measurements at very close range. When I look at the phase noise with Linrad, I can see that at 1 Hertz the 3 crystal oscillator is about 3 or 4 decibels better than my reference oscillators. But at 10 Hertz the difference is much larger, from 135 to 150. And at higher offsets, I can see here at 1 kilohertz, well, at 500 hertz, here it's below 170. 500 hertz, 170, that's here. So here it is very far below my reference oscillators. Now I don't think this is real. I think the phase noise I see here is not only from the reference oscillators. It has a contribution also from my mixers, the Schottky diode mixers, that they think they give some phase noise also. Anyway, I should get a significant improvement very close to the carrier, and particularly below 1 Hz, which will help to make this converge faster. I have disconnected the first stage. That means disconnected the drains of the 3 FETs from this point. Then I have added 5 turns on the T80 core and connected here a signal that I'm using together with the tiny PFA to measure the phase shift from here to the output of the box. And I have adjusted these 5 turns to provide exactly the same output level as I had when the unit was running as an oscillator. Here is the Allan deviation, and you can see the blue trace is an old recording, and this one I have run without the amplifier, just the system, and I call that nothing, July 15, which was when I did that. And then the first recording, the green trace, that was, I had forgotten to adjust the power supply, so I had 16.7 volts. Then I have adjusted the power supply to provide 16 volts to the box. And there is a small difference at up to 100 seconds. When I look at phase difference versus time, I can see that the red curve has a problem. That is, the room temperature has changed. So I look at some section where that is not a problem, let's say here. And then you can see with nothing, there is very little noise. And the green trace is more noisy than the red trace. The characteristic time for these variations is about so as this size, and that is 3 minutes. This is my power supply filtering. 28 ohms and 4 capacitor groups, adding up to a large capacitance. To start with, I have disconnected all of them, so there is only the 28 ohm resistor. And that gives me the bright blue trace you can see here, and it actually looks less noisy than what I had with the capacitors in place. And that is more clearly seen if I magnify a short section like that. It is noisy. It is noisy in a different fashion. Maybe more temperature and less power supply noise. Well, I will connect one of the capacitors now. I have tested the 4 capacitor blocks one by one, 4 different ones, and then all of them in parallel. The curves look fairly similar. From the phase versus time, it's hard to say anything. These slow variations is the temperature that varies. Sun goes up and down and so forth. Hits different windows. I have looked at the voltage drop across the 4.7 ohm resistor, and it gives 16.006 when there is no capacitor in place, and it's a little bit smaller with all the with the different capacitors. These, the oldest and biggest ones, have a very low leakage current. These ones, 40 fairly new capacitors, give a higher voltage drop, but still small. So It is not leakage current in capacitors or not in the Zener diodes. The problem is elsewhere. I can look at the Allan deviation also. Interestingly, it seems that the best result, means lowest number here at 30 seconds, is without any capacitor. And there is a factor 2, more noise when all of them are in parallel. That's odd. I don't know if I should trust that. Probably not. I have disconnected the third stage by cutting this wire here and then looking with the tiny PFA at this point for the phase shift through the second stage only. I made a couple of measurements at different supply voltages. I have kept the old nothing, that's the system performance, and also the entire box, which is this curve. And then these are with different supply voltages. As it turns out, going from 16 volts here to 9 volts, it's from here to here, and then 7 volts, it's even a little better. And to verify that this is not some aging or whatever, I remeasured the 16 volts once more. That's the brown curve, it's here. So these are two measurements at the full supply voltage, and these are at lower voltage. That's a bit unexpected and interesting, because the power level at the second stage is low. There is no problem running it at a lower voltage. But the impedance may change when I change the supply voltage, and that may affect the impedance seen by the crystals, which means that the Q of the crystal might change. I will have to look at that later on. Instead of feeding the second stage through this 5-turn winding here, I have cut this wire, and now I feed here through a 100 ohm resistor. That gives exactly the same level out as I had when feeding here, so the amplifier is operating at the same power level as in normal oscillation mode. So now I'm feeding on the sources instead of on the transformer. And I have two cases, full voltage, 16 volts, that's the green here, up here, and 18 volts, that becomes 16 with the resistor in the filtering for the power supply, that comes here. So feeding on the sources rather than on the transformer gives a significant improvement when running at 16 volts. And running at 7 volts, there is also an improvement, although not quite as large. It's from the red trace here to the blue trace here. Until now I've been using my Wenzel oscillator with the tiny PFA. But this last measurement, which is the same as before, but now I am using the oscillator of my 2-channel receiver, the channel 2 oscillator, which is the best one. And that has allowed me to use the full signal level into the tiny PFA, and that affects the result close to the carrier. You can see the red trace is a little bit below the green trace here. And all the way up to 10 Hz I can see this difference. And then at very large times, there is a problem today because it's very hot outside. So if I look at the phase difference, you can see that the temperature is rising. significantly. It is now 1 o'clock in the middle of the day, and this is bending slightly. It will go down if I wait long enough. Or rather, I have stopped the measurements, so I would have to restart, and then I would see it is coming to be flat. But that will not affect what happens at short times, only long times. I had my lunch and restarted again after about half an hour, changing nothing. And that gave me the bright blue trace, which goes flat. The temperature was constant for 3 hours in the afternoon, obviously. When I look at the Allan deviation, it doesn't differ much. Up to 10 seconds, these two traces with the second oscillator are identical. But at 100 seconds, well, differences are small all the way up to several hundred seconds where the red trace misbehaves a bit. I have again made the input to the second amplifier on the transformer. So I'm repeating the measurement I made before, but this time with the channel 2 local oscillator. And as I can see, those traces are very close. Although they do differ here at very short times. 2.5 now, 2.87 before. And 2 seconds, 1.2, 1.35. But at longer times, they are very similar. And at very long times, they are quite different. Now, that is not any problem. The reason is, as you can see when I go for phase difference, here, it is now 1.5 hours to midnight, and the temperature outdoors is going down fairly rapidly. And it is also going down here inside. And here is when I enter the room and stir the air here a little bit. I did this because I had a feeling perhaps that selectivity in the box would make it very sensitive to the frequency of the oscillator in use. But that seems to not be the case. The purpose of this series resonance here is to present a resistive and as low as possible impedance in this point to the FETs of the first stage, in order to make the impedance seen by the crystals as low as possible. The coil is slug tuned. It's a piece of copper that can be moved up and down with a screw. When I turn that screw one turn, the phase goes from just before I do it, nearly 0, and after one turn, 1.5 times 10 to minus 10 seconds. When I look at the phase shift through the amplifier, this is over 1 megahertz span, and when I turn that coil one turn, the difference is from 92.973 to 92.598. So that is 0.4 degrees. It means that, considering the slope here, small frequency changes on the oscillator I'm using for measurement does not matter at all. The coil is here, connected to the resistors and capacitors to the FETs that are glued to the copper on the bottom of the box. And the coil is tuned by these polystyrene capacitors. One is 300 pF and there are two of 4.7 pF to make the tuning slug come midway on the tuning range. This wire just hangs in the air in the neighborhood of the resonator. I have it like this for calibration of open in the network analyzer. I have connected this point to ground. That is the capacitor side of the series resonator. And I have also connected the network analyzer to the same point for calibration of 0. For calibration with a load, I just put a dummy load directly on the port of the network analyzer. And now I can see the impedance at 10 MHz. Something is very wrong. When I measure the capacitors only, I see 77 pF and very high losses, 25 ohms in series. Seems I have destroyed these capacitors by soldering too close to them. Maybe I have done it now, or maybe it is a long time ago. I will put new capacitors there and check tuning. A new capacitor in place. And the network analyzer tells me this capacitor is 333 pF and with a loss of 5.8 ohms. Here I'm looking at the impedance on the drains of the FETs, and that looks completely wrong. The minimum is here, that's 5 MHz. At 10 MHz the impedance is nearly 3 kilo ohms, while here it is only 600 ohms on the drains. I have reduced the number of turns and made a capacitor 100 pF, and this is polystyrene. And now I see the impedance on the output of the first stage on the 3 drains as it was originally, about 800 ohms and with a minimum at 10 MHz. Well, it's even a little bit better than 800 ohms, it's 750 now. I have disconnected the coil from the transistors, the input to the sources, and then I measured the impedance on the coil to see the feed impedance to the grounded base amplifier. And as you can see, it is very high, 14 to 16 kilo ohms, but there is a sharp something at the center. The span is now 200 kilohertz, means the gain of this stage should be very low, plus minus 20 kilohertz, because the input impedance to the sources is extremely high. Here is the impedance feeding the second amplifier stage, and it is 1.7 kilo ohms. It is far too high. I don't understand why it is this way, because as I can remember, this was quite different from before. Anyway, the impedance loading on the first stage is a bit lower than required. I could go for 1.2 kilo ohms or something like that, and that would make this impedance much lower, I think. So I will change the number of turns on the transformer. I have changed the number of turns from 50 to 56 and from 15 to 11. This has changed the transformation ratio, of course, and I have to change this capacitor. It's now 136 pF, means 2 times 68 pF. Here is the impedance seen by the second stage, 710 ohms, and the sweep width is 100 Hz. And here is the same thing, but now the sweep width is 200 kHz. And here is the impedance at the drains of the first stage. It is 1.9 78 kiloohms. Here is the phase stability through the entire amplifier, through the crystal filter and everything else. And the top curve is an old one. That was when I tested capacitors for the power supply. And now performance is much better, particularly at 30 seconds. I made 2 measurements at the main output. The red curve is at lower power supply voltage, 7 volts. And the green trace, the dark green, is at 16 volts. And the bright blue trace, which is the same as the green, is at the limiter output with 16 volts supply. And here is the phase versus time. The blue trace is nothing, just a BNC to BNC female. And here is what I had when doing the measurements for various capacitors on the DC supply. And the red is at a low supply voltage, while the green and the magenta, they are at 16 volts. And the cause of this noise, it has a characteristic time, roughly from here to here, 6 minutes. My 3 crystal unit is now running as an oscillator. And this is what I see. And I have saved some old. This is from May 22. In this video, I don't exactly remember, but it's the latest I have saved. And you can see that at 100 kilohertz, it is now significantly better, minus 177. And previously it was minus 170. So I have gained 7 decibels. Part of that is because the output level is now 3 decibels higher. But another part is better performance of the second amplifier. I mean, how the mismatch is different on the carrier and outside the frequency of the carrier, I think. And it's interesting to see here there is some curvature, but now the new measurement, it looks more like a straight line here. But I haven't waited long enough to see what happens up here, where there is probably an improvement. Well, here I can see certainly there is an improvement. But you can see here the imaginary part is equally strong as the real part, so this is not a valid measurement. While here it is a valid measurement and it looks higher. So the instabilities I had, they were on longer times than 10 seconds, and that's why I should expect an improvement here. In this range there are a lot of spurs. This could be because I have set with this new measurement a size of 512 for the Fourier transform, thinking it might perhaps make convergence faster. But I feel now that with a smaller transform, the spur removal is not as efficient, because here are a lot of internal spurs of the PN2060. So I will change the transform size and see if that makes a difference. I have Linrad running in parallel, showing Allan deviation. And here I can see frequency as a function of time in this graph. And I have to magnify the Y scale a bit. It is a little bit too hard to see here. So I make it 5 times expanded. And then we don't see so much, but it's clear that the green trace is far more noisy than the red trace. And the correlation between the noise on these two tracks is not very strong, which means that the oscillator under test is better than both of these oscillators. But channel 2 is significantly better than channel 1. And we can see that in the Allan deviation. Channel 2 is below channel 1 by a factor 1.5 approximately. But somewhere near 50 seconds, the traces start to approach each other, because the time constant in the phase locking of channel 1 is much shorter than it is for channel 2. So it means that at this point, channel 1 is following the rubidium source pretty well, while channel 2 has its noise, and at very long times, both of them accurately follow the rubidium source. And why the curve bends up here, I don't really know. The frequency is drifting linearly with time. That is the temperature changing. It is fairly late in the evening right now, so it's getting colder in the house. And the noise, it has an amplitude of about 0.8 millihertz peak to peak. And the period time is fairly long. Let's say from here, 2,500, and the next peak, 5,000. So it's 2,500 seconds between these two, and from here to here, about 2,000 seconds. But the noise is much smaller than the linear frequency drift, so if I select Hadamard deviation, it should look significantly different. And here it is. And it is, if I look at 2,000 seconds, here it is 7 times 10 to minus 11. But the Allan is 9.7. Well, it's not very different. Differences are much bigger at 200 seconds. Goes from 5.7 times 10 to minus 12 up to 1.6 times 10 point minus 11. And it's interesting to see that in the Hadamard deviation, the difference between the channels is more significant, because it doesn't anymore look at the linear drift with time. So this measures how noisy the oscillators are. Now, 1 hour past midnight, the temperature is less varying. I have expanded the vertical scale, and here we can see much more clearly what the noise is and what the temperature drift is. I have set the FFT size to 4096. That's 8 times more than 512, which I had before. And it looks much nicer here. I will wait until tomorrow to see some what the phase noise is at 0.01 Hertz, and then statistics will be better here. Here the imaginary part is not well below the real signal, So this is not an accurate measurement. But it seems that the bigger FFT size makes the spur removal far better. With 4096 for the Fourier transform size, as you can see here, the region from 100 Hz to 1 kHz looks perfectly okay. There are many spurs, but we can see the proper noise floor in between. The previous measurement, which I forgot to save, so this is from the video, it looks ugly. It's hard to judge where the noise floor actually is. One would guess somewhere here, but this is much clearer. But this old, it was with 512 for the Fourier transform size. On the other hand, for very close range, this old measurement was much faster here. With the 4096 transform size, I got only 4 transforms, so statistics is very poor. Although this was a much longer time than this, which had collected already 13, and gives a more reliable result probably. Now they don't differ very much. It says about 40, and the new result is about 40 also. Here it's easy to see that channel 1 is much more noisy than channel 2. And it's also clear that the oscillator under test is better than both these oscillators, because the correlated part is only very slow variations. The fast noise is not correlated to any large extent. I have placed a 50 ohm dummy load here. That is the output from the limiter. The connection from the limiter to the input goes with the coaxial cable internally. As a result, the power level is 4 decibels lower. And if I compare with the previous result, I have lost 4 decibels here. 78.2, 74.5. But the interesting thing is, I have lost 4 decibels all the way, on all the markers. 74, 78, 71, 72. That is a small difference at 1 kHz, because there is a spur there. But if you look, it is 4 decibels. The maximum drive level is 100 microwatts for each crystal. So I measure the impedance on the resonance and off resonance and find 48.63 and 51.33. Off resonance 51.33 ohms. On resonance the same resistance plus the load of the crystals that come in parallel. And the impedance seen here is 48.63 ohms. So I do the usual math and find that X is 924 ohms. On the resonance, each crystal is 80 ohms, and I want 100 microwatts. The amplifier has an input impedance of 24 ohms, so that will get 30 microwatts. Means I want 390 microwatts in 924 ohms, because I have 3 sets of crystals and amplifiers. So I can compute the voltage, standard formula. It is 0.6 volts. And then the power developed in the resistor, the 51.33 ohms, will be 0.007 watts, 7 milliwatts. So the power I want to send into the unit is 7.39 milliwatts or 8.66 dBm. And in a 50 ohm load, because I will measure the signal I'm sending in with the oscilloscope at 50 ohms, which is the most accurate instrument I have for power measurements, I arrive at, I want a voltage 0.607, which is 1.72 volts peak to peak. Here is the reference signal from my Wenzel oscillator that I have been using and set to fit the power of the crystals. But it is a little too low, it's 1.62 volts. And now I have increased the level just a little, 0.8 decibels about. When I send that signal into the unit, this is what I see at the output, 4.52 volts. I have connected the feedback cable and I find I have a little too high power, so I decrease the coupling capacitor just a little. Like this. I have added two back-to-back capacitance diodes here, coupling to the tuning through 3.3 pf. And then there is a 15 megohm resistor to a voltage divider to make sure that the voltage in this point is not undefined when I disconnect the frequency control cable from here. I have added a couple of capacitors to get the frequency very close to 10 megahertz. It is now 4.5 millihertz below. Here's the frequency. And I know that 10 megahertz, my references are very close to 10 megahertz because they are controlled by a rubidium source. And the result is discouraging. Here the noise is okay at wide separations, but when I compare with the previous result, I see I have lost significantly here at 1 hertz, about 4 decibels, well, 3 decibels, and here even more. And interesting is that here at 0.01 hertz, it seems I have not lost anything, although I have only 2 averages now. And this has been running overnight. It is very slow because I have a large Fourier size, 4096. And that doesn't seem necessary anymore because the spurs here seem to have disappeared. This was the old fine measurement and the new, which is degraded slightly, but the spurs have disappeared now that the frequency is very close to 10 megahertz. The capacitors in black, they are the start configuration. I had added 2 polystyrene capacitors, A and B, long ago to get the frequency at about 12 hertz above 10 megahertz. And now I have added 3 more polystyrene capacitors, plus 1 NPO ceramic capacitor. And now it is noisy, the oscillator. I will remove all fixed capacitors and tune for the appropriate output power, and then add capacitors to bring the frequency down, and adjusting here to keep the proper output signal level, to see if I can find what is noisy. These are all the fixed capacitors. I will tune the oscillator to run at the appropriate output level only using the trimmers. Without any fixed capacitor on the crystal, I have to set the coupling capacitor close to maximum and the tuning to minimum to get the correct power. Then the frequency is 83 Hz above 10 MHz. Now the result here, if I compare to the previous measurement, is the same error as I saw with all those capacitors. Particularly here, the noise is about 10 decibels higher than the original measurement. And here, well, the power is a little bit low, but it looks the same. And here, characteristically, as in the previous case, the noise has not increased at 0.01 Hz. This makes me think the problem is elsewhere. I actually made another change in the unit also. The third amplifier was primitively built with the transformer hanging in the air in its wires. I mounted it properly, and that shouldn't make any difference. But one more thing, I routed the wire to another BNC connector. Maybe this problem is just a connector problem. I will clean the BNC carefully and see if that makes a difference. Well, I don't think this will help. The pin to the left is unused, and the other two were used to clean this connector. And as you can see, there is not much of the black dirt on them. It is usually much worse when a problem occurs. The pin in the middle is used to clean the center pin of the male connector. Well, rather soon I can see this did not help. On the contrary, it seems to have made things worse. If you look at 1 Hz, this is what I have seen now. And this is my reference, minus 122, which I had consistently before. And now it is minus 106.7. So this is a very big loss. And there is a loss here also. And I don't have to wait to see what happens up here. It will take a long time. I have connected the tiny PFA to look at the phase stability through the amplifier. And I'm injecting a signal on the T80 transformer, like I have done before. And it is not stable yet. Temperature is rising somewhere. But it doesn't look noisy at all. It looks like a soft curve. Compared to what I had early in this study, it is clearly much better. And this measurement that I believed was through the crystal filter cannot have been through the crystal filter, because from the settings I find when I restart the tiny PFA, I was using the channel 2 oscillator for this measurement. So it must have been either on the transformer or perhaps on the drains on the FETs. So these measurements should be compatible if the amplifier has stayed as it was before. I can look at the Allan deviation, and indeed it looks like the new trace is fairly similar to the green one. I will have to wait for a while and restart to have a curve that does not deviate from a horizontal line as much as this one does. You can see the derivative is steeper here than here. and it has been running for 10 minutes, so it will need half an hour or maybe an hour before it becomes reasonably flat. When I look at the Allan deviation now after 3 hours, I can see that there is some extra noise between 1 second and 10 seconds. It's about the width of this screwdriver, and that is the same as about going from 3 to 4. That's 30% more noise. And that doesn't seem to explain the problems I see, although this is a problem. I have connected nothing to see what happens then. It's this black trace. It has been going 3 minutes only, and I already see that it coincides with the green trace, which is the measurement I had before through the amplifier chain. So something has gone wrong with the amplifier chain, but when I look at longer times, it is even a little bit better. The red trace here is below the green trace I had. So, well, I will continue to look at various things. In order to look at the different stages of the output, the second or the third, I need a bit more power into the tiny PFA, because the gain will be too low otherwise. And then I have to compensate with an attenuator into the box. So I have inserted a 10 dB attenuator here and changed the settings of some attenuators to the inputs to the tiny PFA. And here is the Allan deviation I see. This is not really unusual. When I look at the phase difference, I see here something is really very unstable. So I will touch that 10 dB attenuator a little. Well, it's outside screen. Do it like this. And I touch the attenuator again. And now it looks perfectly stable. Well, reasonably stable. It is very unstable still. I switched the attenuator up and down several times. That was the attenuator directly from the channel 1 oscillator. And you can see I have a new situation now. I still have a severe noise problem. Looking at the phase versus time, it looks like this. Really ugly. I zoom in into this region. And then I will touch the cable coming from the channel 2 oscillator, the BNC connectors of it. Oops. Well, that was my feet on the floor. So something is a loose connection somewhere. Okay, I will hunt for this. Now the tiny PFI setup seems fairly stable. I just started it. It has been running for 22 seconds now. You can see the new black curve coming here. I will wait for a while to see if there are some instabilities coming up. 3 minutes is enough to see that now it is stable. And now the signal goes through the amplifier. The tiny PFA system is reasonably stable now. I found a loose, not properly tightened SMA connector. That was the problem for why it was so sensitive to vibrations. And there was also problems with the variable attenuators. I turned them back and forth several times to find stable positions. And now I compare the now running, which is black, to the red, which was the good measurement, which I thought originally was through the crystal, but which turned out not to be through the crystal. And with this performance, I had very nice phase noise. And that should be the same now. And if I look at phase versus time, the black curve which is now going on, and I'm comparing it to the red one. And you can see there is some drift. And I don't think it's temperature. It's some relaxing of tension in connectors and cables and attenuators and whatever. And looking at the longer time scale, you can see the steeps upwards. If I wait long enough, this will flatten out and become more close to the red trace. So I do not think that this could cause the up to 15 decibels increase of phase noise that I have seen. So there is something else, something near the crystal, presumably. Here is transmission through the box. Q is 1.08 million, and that's normal. So the problem is something else. There are not many components involved. One problematic is the coupling capacitor. So I have avoided using the normal connection to it. You can see the red wire going from the input connector to the capacitor soldered here. And I'm not using the normal input here, it's hanging open in the air. And that's to avoid noise, because I have seen noise from this kind of capacitor in the past. And then there isn't much more. There is a wire from the capacitor to the main trimmer. Very difficult to understand what could have become noisy among those components. And all the rest here, I haven't touched any of it. I have reheated all the solder joints that I touched when removing those capacitors. And then I run again. The frequency is 82.9, so it's very similar. Something has moved just a little bit. It was 83 before I did this reheating. But performance has changed significantly. If I compare with the old measurement here, 1 Hertz, it's the same. Here, there is an improvement. This is the 12.5 Hertz, and this is the 82.9. And even here, but it's small. And here, the noise is slightly higher, means the signal level is a little bit lower. But at 0.1 Hertz I have lost significantly. It is now 83. It was 89 before, according to this table. But at 0.01 Hertz there seems to be a small improvement, but statistics is not good enough to say anything sure about that. It is very slow to collect this when using a big transform like 4096. I have put back the capacitors A and B, and then tuned for the same frequency and a similar signal level. And here is the result, and it differs very little, as you can see here, from the good result I had before with exactly the same capacitors and settings. There could be a small loss here, hard to say because of the poor statistics. And here the noise level is a little bit higher, means the signal level is a little bit lower. But it seems whatever was wrong is no longer very... I have added sealing strips to prevent infrasound from entering into the box. And the lid is now from 2 mm aluminium, which is much stiffer than the 1.5 mm PCB material I was using before. It's hard to say whether there is really a difference. Here is what I see, measuring the sealed box. And here is what I had before. And now there is no degradation at this point anymore. It looks that it might be 1 decibel better, maybe. And at 1 Hertz, if you compare this to that, maybe it is a little better. The number of averages is not as large, it is 35 here, and the old measurement was 51. And it looks like there is a half a dB or maybe. Anyway, now I have restored the performance I had before. And here, but looking at this, there are circles in the measurement points all the way. So these values are not correct. They will go down with more averages. Now there are only 2 averages, and I don't want to wait several days to get a reliable measurement. Well, I could make a measurement with a smaller transform size, perhaps, but that's not important at the moment. I'm happy with it as it is. It will be a good channel 1 local oscillator for my test system. I put back all the capacitors, including the small one to the varicaps, and the result is really discouraging. This is what I have, and this is what it should have been. So I have a 20 decibels loss caused by something. And it is around the crystal because the flat floor is the same as before. I have removed the 3.3 PF ceramic capacitor, and it is obviously much better now, even though the statistics are not very good. This is my reference result, and here is what I am getting. So I will put some other capacitor for the frequency control. I have 4.7 polystyrene, so I will put one of those there. It is definitely clear that this 3.3 PF ceramic capacitor is really bad. I have used 1 PF from the same source, and they were good. That's why I choose this one. but that was a bad choice. Now the frequency is 10 MHz plus 0.081 Hz. That's well within the control range of the capacitor diodes. The noise is low, but not exactly what I saw before, in the range around 100 Hz here. This is the old result. It's 1 or 2 decibels better. That was at 12 Hz above. Now it's unclear whether this really could be caused by my oscillator, because in this range the noise comes from flicker noise in the second amplifier probably, but that should not have changed. But other frequencies, performance is very much the same. Now, the reason that the value I see at 100 Hz is minus 165 dBc per Hertz, it could be that the system noise floor specified for the PN2060A should be minus 165 at 10 MHz. And there is a typical noise floor measurements self-correlation that shows minus 169.7 here, but the curve is rather noisy and it's a little bit hard to say what the actual value should be. It was 40 minutes only, and that's not enough for this kind of measurements, I think. Anyway, I will use this as my channel 1 oscillator, and I will get more understanding of what performance it might have. Here is the Allan deviation. You can see how very stable the Wenzel oscillator is over long times. I can compare this with a previous measurement of my own oscillator, which is drifting with temperature. But the important thing is the noise of the channel 1, the green trace, as compared to what I have now. And the difference is not very large, but the noise is a little bit lower. You can see in the Allan deviation how the noise is improved. You can see the green trace. Here is what I see in 10 minutes. This is the new oscillator, and here is the old one. And there is a difference around 5 to 10 Hertz. I hold the screwdriver on minus 136 dBc. And as you can see, it is between 135 and 137. It is a little bit vertically shifted. I will try to do this more accurately. No? But you can see the green, channel 1, it comes down significantly and to the same level as where channel 2 is. And the same here. But very close to the carrier, you can see the yellow track is better here. This is the Wenzel oscillator. The green has come down also. So this is a slightly better oscillator, not much different, but I will go and use this for the future, and then I will start some other interesting experiments.